I don't need a paper copy of your work if I can see the picture. So for example, if you turn something in at home outside of class and you use your cell phone and take a really clear picture, that's great. I don't need the paper copy then. But I do if you turn something in class using your Chromebook, because Chromebooks take these blurry pictures. Anyway, we can talk more about that if you want, but just remember the comments. And then the other thing, so I want you to pay very close attention to your reaction to what I'm about to show you, okay? And depending on your reaction, it really is going to determine what you do to deal with it, okay? So here it is. There is going to be another tracker quiz. So pay attention to your reaction there, because if your reaction is, okay, then you're in good shape. Like, it shouldn't feel like, yeah, exactly. What it should feel like is if I told you I'm going to test you on your ability to use a compass to measure angles. Like, all of you are not compass, a protractor is what I mean. A protractor to measure angles. You can do it with a compass too, but I meant a protractor. So if I gave you an angle and a protractor right now, and I said it's 10 points, you gotta tell me the angle, within 2 degrees, you'd all be like, okay, and you just do it. It's not scary if you know how to do it. So if your instinctive reaction was, oh crap, then what that tells you is you don't know how to do it yet. And if that's you, I will help you. You can reach out to me, I'll work with you. I'm gonna post more practice videos. I'll go through it with you individually. I'm not gonna go through it in class because 80% of you know how to do it, but I know that 20% of you aren't there yet. I see it. I saw it in the makeup quiz yesterday. I see it in your day-to-day work, and you gotta be able to use it to find the stuff that we need. So just a second. Trey, you had a question first? No. Are you good? Okay. Yeah.
Is it going to be on the same stuff, or is it going to be different?
Nope, same idea.
Okay.
Yeah, this is all we need to do, and I know that for those of you that haven't quite nailed it yet, that's like, okay, that's great, but that's a lot. I do understand that, but I'm not going to add anything. You need to be able to find accelerations of things during periods of constant acceleration, and you need to be able to find how fast they're going. Now we're dealing with 2 dimensions, so in either dimension, you got to be able to find how fast it's going at any time. Think about it like it's our speedometer. That's what we're doing with Tracker. We are using it as a speedometer for things that don't have a built-in speedometer. So if somebody kicks a soccer ball and you want to know, hey, I wonder how fast it was going, up at this angle, a second after it was kicked. You can use Tracker to do that. Yeah.
So like the first quiz was like just 1D, now
it's so it was always 2D, and it was always that but Tracker tells you information about one or the other dimension. It doesn't give you like 2D information at the same time. So it's not going to really feel any different from what we've done already. We've been working with 2-dimensional motion, even with Tracker. It's just that you've been looking at one dimension at a time, which is how you use it.
Are we gonna get our quizzes back from last time to see?
Yeah, I'll go. So I haven't looked at them yet, but I'll go over them and I'll give them back to you, and you will have time. Like, I'm not gonna unfold this on you today, and honestly, I'm not gonna unfold it on you this week because I want you to have some time to practice if you need it. But what I am gonna do, it's not a pop quiz, but what I will say is, starting next week, be prepared, because if we have 15 minutes, like if there's a time, and it's like, this is it, then I'm going to use it. So I'm announcing now that, by next week, by the start of next week, you should be ready. My suggestion is you should be able to, just practice a whole bunch of times. It doesn't take very much time if you really know what you're doing. So the first couple of times might take a while, but then just a few minutes. You can do the same video over and over again. It's the steps involved in getting the measurement that are important. And then the last piece about that is that depending on what I've seen so far, I may actually sit down with you individually and ask you to do it, because for some of you, part of my problem is that you're coming back with information, but I can't tell whether you actually know what you're doing, and you're just like, sometimes the things you write don't quite make sense to me, but then I think maybe you do know what you're doing, but you're just writing down the wrong thing, and I can't figure it out without sitting with you, so I may ask to do that. All right, that's that, and we can talk more about that later. Next, I want to I'm going to go through two problems really quickly on the predicting projectile distance. You can check your own work. I know you've turned that in, but what I hope, I think you turned it in, right? I had you turn it in. Pretty sure I had you turn it in. But what I hope, and actually I created that, so I can give that back to you. What I hope is that what you see is super familiar. I'm going to go really fast. I'm going to go do two of them, one with a horizontal angle, one with a vertical angle, or with a non-horizontal angle, and because I want you to see exactly what it should look like. And this is not just for this particular assignment. This is how we solve all two-dimensional kinematics problems, okay? So let's start with this one. So it's a horizontal launch angle with a height of 0.9 meters. So I always do the same thing on these, which is I start with a picture. For my projectile launcher stuff, my picture always looks the same. I just draw a little tube, and there's the ball, and it's going to fall to the ground. In this case, it's 0.9 meters above the ground, and what I found the other day was that from the video that I made, it looked like my initial velocity was about 4.5 meters per second. You might have used a different number, and that's fine. You're not gonna, if you start with a different number here, you're gonna get a bunch of different numbers everywhere else, but that's no big deal. So what we're trying to find is this distance right here, and I'm gonna say that my 0, 0 is on the ground directly below where the ball starts, and I'm going to say that I'm using a standard Cartesian coordinate reference frame where up is positive to the right is positive. Because this is that basic how far does the projectile go problem, we always start in the y dimension, and what we're going to do is use that to find how long it's in the air before it hits the ground. So it starts at 0.9 meters, it lands on the ground, the initial y velocity is 0. I don't even need to use the vector solver for that. Why? Because we're told it's a perfectly horizontal launch, not moving up or down at all to start. I don't know how fast it's going at the end, and I don't care. The acceleration is -10 meters per second squared, and the time for that I can find using the kinematic solver. And those of you who did the algebra, if you did it and got the right answer, fantastic. And if you didn't, it's no big deal. So that means it was in the air for about 0.4 seconds. And I'm just going to round it because it does not matter at all whether we use 0.4 or 0.42 or whatever. It's not going to make any sort of appreciable difference. Now that we know the time, we can figure out how far it moves horizontally during that time period. And there's some stuff that we know already because it's projectile motion. One is that whatever its initial speed is will also be its final speed because there shouldn't be any acceleration. And you'll see today in the work that you do, you actually, there is acceleration, and you all know this, right? Because did I do this? Did I already demonstrate this to you? Like for the crumpled up paper towel? Like, clearly this crumpled up paper towel is not moving at a constant rate in this direction because of air resistance. The projectiles that we're shooting have less air resistance than a crumpled up paper towel, but there's still some, which means in both vertical and horizontal dimensions, our accelerations aren't really going to be what we think they are. Some of you are gonna take that into consideration in the work that we start doing today, and others of you are gonna ignore it. You always have the option to do either, and I'll explain in a little bit more detail. But for these theoretical problems, we know nothing about air resistance, so we're just gonna go with what we've got. We also know that it starts at position 0 and that it's in the air for 0.4 seconds. And some of you probably figured out that we don't even need to use the solver for this. The distance it goes is always time times the velocity. And that is only true for this specific kind of problem, but it's always true for this specific kind of problem. So that means it should have moved about 1.8 meters horizontally, if I did my math right, which I maybe didn't, but none of that is super important because this is the correct physics, okay? Any questions about that? The other, so the first 3 problems on predicting projectile distance all involved a perfectly horizontal launch, which means this is the only thing that should have changed from your initial variable setup. Everything else would have looked the same. This distance would determine the time, this time determines this time determines the final position in the x dimension. If this all makes sense to you, that's really good. If you can muddle through it and get an answer, that's not bad. If neither of those things is true, then this is going to take you some thought. You're going to have to, outside of class, continue kind of pondering and thinking about it, and I'm happy to help you with that. Okay, let's do, that's not it. Let's do this one. So let's do a 35-degree launch angle with a height of 0.75 meters. So my drawing, basically the same, only it's tilted. So now it's at a 35-degree angle. My initial height is 0.75 meters. The ball is going to move in a path where it's still a parabolic arc, but now it goes up a little first before it comes back down. This initial velocity, which I'm drawing as an arrow that starts where the ball starts, that's pointed in the correct direction, but real velocity factors have no location. They don't have a start, they don't have an end, but it's very convenient to draw it like this. So this is what my initial velocity vector would look like if I represented it as an arrow. We're still looking for displacement. I'm still gonna have 0, 0 be directly below the ball on the ground, and I'm still gonna use the same standard Cartesian coordinate reference frame. Okay, so all of that's the same. The big difference with these is that I have this initial velocity that is not either in the y dimension or in the x dimension. So before I do anything else, I've got to figure out how much of this is just to the right and how much of this is just straight up. So I do this the way that I told you. I draw a picture, I'm going to put my angle on there, I'm going to put my vector magnitude on there, and what I'm looking for is the magnitude of the vector represented by this arrow. That's going to be in my positive x direction, so that will be my initial x velocity, and the magnitude of the vector represented by this arrow, which is going to be in the positive y direction, and it's going to represent my initial velocity in the y direction. So for that, I do need the vector solver. You can do it with trig too, of course. But the vector solver is pretty quick. 4.5 at a 35-degree angle up and to the right is, up and to the right. So that's 3.7, 2.6, right, roughly. So 3.7 in the horizontal direction, 2.6 in the vertical direction. Where this is going to change my variables is I'm not going to use this 4.5 anywhere. It's moving at 4.5 meters per second for sure in real life when it starts moving, but it's not moving up at that speed and it's not moving to the right at that speed. So my y dimension variables, which I still start with because this is the same sort of basic problem, my y dimension variables are going to look like this. My initial position 0.75 meters. My final position is when it hits the ground. My initial velocity in the y dimension isn't 0 anymore. It's going up at first this fast, 2.6 meters per second. If we took that launch, which is left to right, and you came around and looked at it from behind, what you'd see is that ball going up before it comes back down. And the speed it's going up at first is 2.6 meters per second. It does not continue moving that fast though, because it's accelerating downward, which means its speed goes to 0 and then it starts increasing in the downward direction. Our goal is to find how long it's in the air with all that information. Think I can remember that? I'm not convinced. It's 0.75, 2.6, is that right? I think that's right. Did I do that right? Anybody see any glaring mistakes there? About 0.7 seconds? Does that work for you all? Tell me if I'm wrong, because I already forget what I put in there, but I'm gonna say 2.7 seconds. Is that what I got? I already forgot that too. Was it about 2.7 seconds? You all are in the same place that I am. No, it wasn't. It was about 0.7 seconds. Oh, poor brain. Do you all like have deep sympathy for what the Swiss cheese intellect that you see before you? Like you have deep, like sometimes you just go home and tell people at home, like, I had a good day at school today, but I just feel so sorry for poor Mr. Bregar. You do that, right, Lillian? All right, so it starts at position 0. The initial x velocity is not 4.5, it's 3.7. It's weird because it's like, how do we know that? And the answer is, we know that because of math and the magic of independent motion in 90-degree angles. Our final velocity is also going to be 3.7. Our acceleration is 0. And our time is 0.7 seconds. So same deal, we just multiply those two numbers and it'll tell us the distance. 0.7 times 3.7 is 2.6, divided by 2.6. And you could use the solvers for that. You don't have to do the math, but that's how it goes, okay? So 6 problems, all of them should look almost exactly like this. Now the other thing that I had you do in these problems was draw position, velocity, and acceleration graphs in both dimensions, which is going to take forever to draw, because I have to draw a position versus time graph in the x dimension and a position versus time graph in the y dimension. I have to make a velocity versus time graph in the x dimension, a velocity versus time graph in the y dimension, an acceleration versus time graph in the x dimension, and an acceleration versus time graph in the y dimension. And you'll see this is going to take forever because the x acceleration is 0 the whole time. The y acceleration is -10 the whole time. This is the first one where our initial x velocity is 4.5 and it stays the same the whole time because there's no acceleration. Our initial y velocity is 0 and it has a acceleration, therefore a slope of -10 meters per second squared. And in the x dimension, it's moving from left to right at a constant speed. Constant speed on an x versus t looks like this. In the y dimension, it's moving from position 0.9 to 0, but it's speeding up as it goes. So, and it lands at 0, so my y versus t graph is going to look like this. See, that took forever. And then if I do the other ones, those are also going to take forever. There's my x versus t, y versus t, vx versus t, vy versus t, ax and yx versus t. My accelerations are the same as they were before. My x velocity is a little bit less, but still constant. My y velocity now starts at positive 2.6, but quickly becomes 0 and then continues in the negative direction. The slope of this line is negative 10. My x versus t graph is still a diagonal line that goes up and to the right. My y versus t graph starts at positive 0.75. It goes up a little bit, and then it starts coming back down. So my y versus t graph looks like that. So that's what we're looking for with predicting projectile distance. If you got the points, then you got the points. This is what you need to be able to do, so make sure you can do that, okay? Any questions about any of that? Okay. Next steps are that we are going to, we're going to do a little bit more. Some of you are in a position where you can do a lot more. And some of you are just going to do a little bit more because that's where you are, and that's absolutely fine. So the next piece that we're going to add is we're going to make a real prediction with a real projectile launcher. Here's the real projectile launcher. It launches the ball at the speed of about, I honestly can't remember, but we have a video to be able to figure it out. Don't worry, it's perfectly safe. That is what it's going to look like. And so to make predictions for this, the first thing, I'm never going to get that. That's going to be like under there until I retire. That's going to be under there until they like bulldoze the school. So the first thing that you're going to need to do is figure out how fast the ball comes out of the launcher. And I said this before, but I didn't really emphasize it because we weren't doing real tests with real launchers, but I'll say it now again with emphasis, which is, it doesn't matter what angle you put it at, it always comes out at the same speed. And that isn't something that's intuitive. Like that, in fact, it's not quite true, but it's true enough. And if you want to talk about it, we could, but that's not something we need to talk about now. Basically, what it boils down to is that we figured out experimentally that if you have a launcher, a spring-loaded launcher like this, that every time you launch it, the ball comes out at the same speed. It doesn't matter if it's pointed up or to the side or somewhere in between. It always just comes out at the same speed. So if we find the speed from a video using tracker, then we know the initial velocity. We might not know an angle for a test, because I could measure its velocity at this angle, and then somebody could be like, okay, smarty, how far is it going to go now? I've changed the angle. The speed will still be the same. So we still know the initial launch speed. We will know the initial launch angle, because the predictions that we make, I'm going to tell you. I'm going to put it at such and such an angle, and your job is to figure out some stuff. Some of the additional things that you're going to need to think about are, number one, we do want to know, it's kind of interesting to know how far it would go if we just launched it. Like just now when I launched it, it would have been kind of cool to make a prediction about where it was going to land on the ground. But we're going to make some different predictions as well. One of the predictions we're going to make is, where would we need to put this container in order for the ball to land in it? And that is almost like finding out how far it's going to go. But it's not quite finding out how far it's going to go. Because if we are trying to get the ball into the container, then we're not aiming for the ground. We're aiming for the top of the container, which is above the ground. This might make a little bit more sense if you imagine a tube like this. If you figure out how far the ball is going to go when it hits the ground and you put the tube there, then when the ball comes in, it's going to hit the side of the tube. That's not what we want. We're not looking to place the bottom of the tube where the ball would hit the ground. We want to place the top of the tube somewhere where it intersects the ball's arc. So that's a little bit of a different problem, and it's kind of tricky. The other thing that we're going to do is, I have a little hoop. It's a ring from a ring stand. And that is going to be placed a certain distance away horizontally from the launcher. And your job is going to be to figure out how high up above the ground, or like up, like how high above the ground, you're gonna need to put that so that the ball goes through the ring. So you're gonna basically launch a ball. The goal is to launch it through a ring and into a container. And we can play around with different launch angles, different launch heights, different containers even. We could launch it into this, or we could, if you want, you could try to launch it into a paper towel roll. Like that is a prediction that you can make. We can put the ring at various distances, so it doesn't always have to be the exact same distance. The idea is, if we can predict the path of the projectile, we can predict where to put buckets and garbage cans and containers to catch it, and we can predict where to put rings and hoops so that it goes through. And so this is a little bit more than what we've done, because what we've done so far is just figure out how far is it going to go before it hits the ground. That's the simplest question. We're adding to that now. Lily?
Are we more doing like figure out the path so then we know where to put stuff, or we know where we want to put stuff so then let's figure out like the path?
A little bit of both. Yeah, a little bit of both. For one of them, you're figuring out the path so you know where to put it. The other, you have to make sure that the path is right. Yeah. The video that you're going to use to find the speed is posted here. And when you watch this, one of the things that you'll notice is, unlike the last video we used, the launcher is at an angle. So when you watch this video, what you'll see is that the ball does not come out at a perfect horizontal angle. You can even see it in this video. You can see that the ball is moving up and to the right. How do you deal with that? In Tracker, we find out information about one dimension at a time. If we want to know how fast the ball is coming out of the launcher, then we want one of our dimensions to be in that direction. So if you take your XY coordinate and just tilt it so that the x-axis is in the direction of the launch, and then use Tracker to find the speed in the x direction, it'll tell you the initial speed of the launcher. Because that's how fast it's going. It's not moving perpendicular to that plane at all. It's moving 100% in this direction. So if we set this direction up as one of our axes, we can find the initial speed with Tracker. I'm also going to ask you to find accelerations in the horizontal and vertical direction, which is not a tilted axis. It's a regular up and down, left and right axis. You don't have to replot the points. Once you get everything set up, you can tilt that axis to your heart's content, and Tracker will adjust the graphs to fit. So you're going to do it once, like this, to find the speed, and then you're going to tilt it, and you're going to find accelerations. What you should see is that the vertical acceleration is close to, but not equal to, 10 meters per second squared down. And the horizontal acceleration is close to, but not exactly equal to 0. When we start making predictions, your predictions could just use 10 and 0, like we've been doing, or if you're up for a challenge, you can try to create a more accurate model, because it's not 10 and 0. It's close, but it's not exactly 10 and 0. You'll get better predictions if you tinker with things a little bit. So those of you who are up for that challenge, I'll help you with it. It's not required, but it's something that some of you will get to. Yeah.
Wait, do you think you would recommend that we do like tilted axis, or we just always keep it straight and then find the speed by the magnitude?
Doesn't matter. Either way will work just great. Yeah. Yep, you can do it either way. And you should get it's probably not going to be the exact same answer, but it should be within well within 1/10 of a meter per second, probably considerably less than that. Other questions? Okay, so this is not an assignment, but it's something that you have to do before you can do the rest of the lab. So the first thing is, don't click this link, by the way. It's the same video, this one's just longer. So use the one that I posted in Canvas. I'll adjust that, I forgot. So first thing is, figure out the launch speed. Second thing is, how can you make predictions using the launch speed if you know things like the angle of the launch and the height above the ground, but I haven't told you yet? Like, what if I say, I'm gonna put it somewhere, but you don't know where, and I'm gonna tilt it at an angle, but you don't know what the angle is? How could you come up with a set of generic equations that you could use to find how far it goes, how high it goes, how could you set that up? So that's a little bit of a challenge. You may not be able to do that, and that's okay. Some of you might be like, well, I know I could put this into Tracker, and that's pretty good. That's not bad at all. But some of you are actually gonna be able to be like, t equals plus or minus the square root of a bunch of stuff, because you have the math chops for that, and that's a really good thing to do. And then you're gonna try to make some predictions, and you can test them, because we have an actual launcher here. So, for example, if you launch it you pick the angle and the height. Like, this isn't a test and it's not an assignment, it's just like, put the launcher somewhere, put it at an angle, measure the angle, measure the height, and then try to figure out how long will it take the ball to be about 20 centimeters away horizontally. How long will that take? What will the vertical position of the ball be after 0.12 seconds? It's gonna, where's it gonna be up and down after a certain amount of time? What will the vertical position of the ball be when it's this far away? So this is like 7 centimeters. 7 centimeters away from the launcher, how high off the ground will it be? You can make that prediction. And how long will it take the ball to be down here, at 20 centimeters below the launcher vertically? Those are all things that you can predict. What you need for that is initial speed, which you'll get from the video, a known launch angle, which for now, you can pick anything you want, 20 degrees, 45 degrees, 11 degrees, try different ones. And a known launch height. This little symbol right here that you can't see, there's a little circle, that's where the ball is when it's launched. So you just measure the distance from this down to the ground or wherever else you're launching to. All right. So there is homework tonight. You have the rest of the period to work on this. And this will lead right into a lab that will start on Thursday, or most of you will start on Thursday.
Is that the lab that's in the module?
That's not there yet, but
I think, is that something lab?
that was this. This is
The
preliminary
different
lab.
Preliminary lab.
Yeah, but this isn't the assignment. The real lab, I'm gonna give you a launch angle, and I'm gonna give you a height, and you're gonna have to figure out where to put the bucket and where to put the ring.